Okay, so in this video, we're going to talk about homogeneous linear systems of differential equations. So let x of t and y of t be functions of t. And suppose we have the following then. So our first equation in the following system, say, first equation is x prime equal a11x plus a12y. And our second equation is y prime equals a21x plus a22y, where here the a11, a12, a21, and a22 are constants. Okay, we're going to write this system in matrix form, so let me do that. Okay, so note our system now can be written in matrix form, it's called. So I'm going to take my xy up here and write it as the vector down below, which I've done here. And then take my two equations and write in matrix form like I've done here. Okay, and then I can write this guy as a11, a12, a21, a22 with the x, y in the outside. And what this means is I'm going to take the x here, multiplied by the a11, and the y multiplied by the a12. And that's how I get this guy here, this row. Then I'm going to go the x times the a12 and the y times the a22, sorry, and add them together. That's how I get the second row of the matrix here. Okay. In addition, I'm going to call, say, this vector over here, the x prime, y prime. I'm going to call it v prime, which I've done down here. And I'm going to call the xy vector over here. Let me erase this. Erase this for now. So I'm going to call this xy vector here v. Then I'm going to call A the matrix, so this guy right here. Doing that, our system can then be written in the form AV equals V prime. So we call this a homogeneous linear system of differential equations. And our goal is to find solutions of the system. Okay. Okay, so let's take a look at an example now. Okay, so here's our first example. Okay, so here's our example. Okay, so the example says, write the given linear system in matrix form, and then show that the vector v1 equal to 1, -1, e to the minus 2t is a solution of the system down here. So x prime equals 2x plus 4y, y prime equals x minus y. Okay, so let's show that now. Okay, let's first write it in matrix form. So doing that, we get the following. Okay, so I've written the matrix form here. So again, I'll take the first row up here, and the 2 will go into first position here. The 4 will go into this position here. Then the coefficient in front of the x is a 1, so that goes here. The coefficient in front of the y in the second equation is -1, that goes here. And I put the x, y in front, then equals x prime, y prime. So this is the matrix form for our system. Okay, now let's show that the V1 is a solution. Okay, so doing that, we get then. Okay, so let's look at the V1 and show, let's look at the derivative of V1. Okay, so my V1's here. Okay, so taking the derivative then of this guy, you'll have your vector in front still, the 1 minus 1. And then you'll take the derivative of e to the minus 2t. So you'll take the derivative of the 2t up there, and that's going to be just -2. So it'll be -2 times e to the minus 2t. And at -2, then you can multiply in with the 1 there and with the -1 there. And so it'll be then minus 2, 2 vector, e to the 2t. Should be a t here. Okay, also note here, if I do AV1, so my vector, my matrix again is the 2, 4, 1 minus 1, and then my vector is 1 minus 1 e to the minus 2t. So when you're multiplying the matrix with the vector, you're going to go 1 times 2. That's how I get this guy here. It'll be negative 1 times 4. So I got the negative 4 here. That will be 1 times 1. That's how I got that one. That'll be negative 1 times negative 1. That's how I got that one. So adding those will become minus 2, 2 e to the minus 2t. And notice here that these two are the same. So this also equals then v1 prime. So we've shown then that our v1 is a solution. So let's write that. So hence we can say then that our v1 is a solution of the system. Okay, all right, so next thing. Okay, so how could we solve this linear homogeneous system in general? So say you're given this matrix in general form. Well, let's assume that the derivative x prime y prime is equal to some constant times my xy. So that would mean then that the x prime would have to go to the lambda x, and the y prime would have to go to lambda y, which I've written over here. So lambda x would equal x prime, and y prime would equal, sorry, lambda y would equal y prime. We can then solve for lambda. So dividing by x on both sides, we'll have lambda equals x prime over x, and lambda equals y prime over y. We can then integrate both sides with respect to t, and doing that then, so we'll get then integrating lambda, and integrating x prime over x, and integrating y prime over y. And recall then, if you integrate u prime over u, dt is going to be ln of u, should be u there actually. We change that. ln u there. So applying that here to our x prime over x and y prime over x, we get the following then. Okay, so integrating the x prime over x, we'll get ln of x. Integrating the y prime over y, we'll get ln of y. And integrating lambda, let's get lambda t plus a constant over here and here. Okay, we want to solve then for x and y, so we're going to exponentiate both sides to base e. So doing that, we get then. Okay, so raising both sides to base e here, which I've done here and here. And the e to the ln of x will just be x, e to the ln of y will just be y. And I'm going to call e to the c1, let's call it k1, and e to the c2, let's call it k2. So then x can be written as then k1 e to the lambda t, and y can also be written as k2 e to lambda t. All right, let's keep going. Okay, so as a vector then, we can write our xy vector. Well, the x can be written as k1 e to the lambda t. So using this up here, that's how I got my k1 e to lambda t, and in place of y, we can write k2 lambda e to lambda t right here. Then I can pull out the e, which I've done here. Okay, so then we have our, taking the derivative of this guy then would be x prime, y prime. So it'll be k1, k2, and derivative e to lambda t will be, derivative lambda t is just lambda. And so it'll be lambda e to the t. So it can be written in as e k1 e to lambda t. Okay, so let's keep going. Okay, so we can say then that if we have our system and our solution xy can be written this way, then a matrix would have to equal lambda xy. And from there we can conclude then, okay, so we can take this guy, cross the equal sign, which I've done here. I'll have then my matrix at times my xy vector minus lambda xy equals the 0, 0. And then we can write this. So again, this means x times a1, 1, y times a1, 2. That's how I got this guy. Then I'm going to subtract lambda x. That's how I got this. Then you're going to go x times a21. So I got this guy here. Y times a22. Then we're going to subtract my lambda y. So I got here. And I claim it can be written like this over here. So let me explain. Because this guy here, we could write as a11x plus, sorry, let's write it as, put all the x's together, minus lambda x plus a12y. This guy we can write as a21x plus a22y minus lambda y equals 0, 0. Okay, so in matrix form, I could take out the x's here, which I've done up here. And I'd have then a1 and a lambda left here. That's how I got that. Then taking out the y here, I'd have the a1, 2 left there. And below, taking the x out here, I'd have the a21 left. That's how I got this. And below here, taking the y out, I have an a22 and a lambda left. That's how I got this over here. All right, so let's keep going. Okay, so we have then that our matrix here is equal to the 0 vector. And that can only happen if the determinant of the matrix is 0. And recall the determinant of the matrix A, B, C, D is pretty much A times D. So I got this guy, then minus B times C. So I got this one. Okay, so like, I guess a little example here. We have determinant of, say, 1, 3, 5, 7, be 1 times 7 minus 3 times 5, so 15. So that would be minus 8. The determinant of that. Okay, so let's keep going. Let me erase this. Okay, so next thing. Okay, so if we take determinant of this guy up here, it would be a11 minus lambda times a22 minus lambda. So I got this. It would be minus a12 times a21. So I got this guy here. And then if you multiplied this stuff out over here, so if you go lambda times lambda, negative lambda times negative lambda, that's how I got my lambda squared. Then you're going to have a a11 negative lambda and an a22 negative lambda. So you can write this a11, a22 with a minus sign in front, lambda. That'll be a11 times a22. And then a21 minus a12 equals 0. So we call this the characteristic polynomial. All right, let's keep going. So we call the solutions of the characteristic polynomial the eigenvalues. And so for each eigenvalue will correspond to a solution of our system, and the solution will be of this form. It'll be k1, k2 as a vector times e to the lambda t. All right, next thing. So we call the vector k1, k2 the eigenvector for lambda. And the eigenvector has the property that when you multiply our matrix here by the eigenvector, you'll get 0, 0. All right, next thing. Okay, so to find the eigenvectors, or vectors, there may be more than one for each lambda. We're gonna have to solve this augmented matrix below here. So this guy here. And the next few videos, we'll look at some examples on how to do this. So I'm gonna leave this video here for now. So next videos, we'll look at some concrete examples. Okay, so let's leave it there.